Hey everyone, my name's Elijah, and I'll be covering the grid shock coordinated load changing attacks on power grids. Um, so a little acknowledgement to the authors, Adrian Dabrowski, Johanna Ulrich, and Edgar Weipel. This paper was originally presented at the annual Computer Security Applications Conference, or at ACSAC 2017. Just so a little bit to begin, electric power grids are considered critical infrastructure. So that's any infrastructure whose disruption could have a severe impact on a nation or society. Power grid providers must continuously maintain a balance between supply and demand, and power consumption is predicted by using elaborate models, but these models use assumptions. In this paper, the authors develop attacks violating this assumption, investigating their impact on power grid operations, and assess their feasibility for today's adversaries. So, without electricity, several critical systems would not be able to operate, right? So think about water and food supply, transport, medical aid, so things like at-home oxygen tanks can't operate without electricity, and communication infrastructure. So companies like Verizon and AT&T, they actually get their power from the power grids, right? And it's because of these things that why power grids are considered critical infrastructure. So electricity consumption is largely uncontrolled, right? So the power distribution companies don't stop their customers from, plugging in the toaster or using their microwave. Under normal operating conditions, when additional power is needed outside of this predicted demand, the remaining energy needs are supplied by the control reserves, which are basically just power plants on standby. In the US, this is called spinning reserves. So what happens when a botnet forces a power grid outside of its typical operating conditions? A little bit of background. So the amount of power in demand on a typical day cannot be stored, so the amount of power generated must be as close to the amount of power in demand as possible. So one of the primary challenges of running a power grid is to maintain equilibrium and to supply only what's needed. During the power production and distribution processes, the nominal frequency, or the ideal frequency, of the power system is 50 Hertz in Europe or 60 Hertz in the US. This paper is going to cover European power grids for the most part. So if nominal frequency comes up in later slides, we're talking about the 50 Hertz in Europe. So if there is more supply than demand, then this frequency rises. Alternatively, if the demand is higher than what is available, then the frequency goes down. So if there's more consumers than expected, if more people are using energy than expected, then we'll have frequency go down. If the forecasted power consumption deviates too much, it can force the power distributor to enact emergency routines to put the power grid back in balance. Remember, the goal is equilibrium. And so these are a couple of the emergency routines at specific frequencies. This one pertains to Germany. But you can see that it doesn't take much, right? So if the nominal frequency is 50 and they're already alerting at 49.8 Hertz, it needs to be pretty consistent. 47.5 being basically a blackout. You're disconnecting all power plants. A little bit more background. So in the early days of power grid operation, most grids were independent of each other, so they were thought of as like islands. There were no connections between any of them. But now things are a bit different. You can have power grids that run basically in parallel. They can work together, and they are physically connected to one another and separated into control zones, which you can think of control zones as basically just groups of power plants separated by geographical location. So in Europe, each of these zones are roughly the size of a small country. Larger countries like Germany will have multiple control zones. And all these control zones comprise the continental synchronous grid. And this is a grid in Europe. It's actually the largest grid on Earth. And in order to function, each zone has to operate at that nominal frequency, or 50 hertz. So if you're on, one side of the country, it's 50 hertz, and it's going to be the exact same on the other side. So if something goes wrong, right? If maybe there's one control zone that can't supply enough power, it might need another control zone to help out, which is the whole point of having these control zones being connected to each other, right? So there's a couple steps to basically regain that nominal frequency. And the first step is primary control. So that activates within seconds of an issue. The main goal here is to stabilize the frequency at a stationary value. The second step would be to activate basically another control zone to help out, and that takes about 30 seconds, and then it'll take a few minutes to fully activate, but this is used to it replaces the primary control and then returns the frequency back to its nominal value of 50 hertz. Lastly, tertiary control, it'll free up the resources from the primary and secondary control, and after this, everything should be back to normal. Okay, so what are the authors trying to do here? The strategy is to use botnets, or zombie computers, to modulate consumers' power consumption in a coordinated way over the internet. The hypothesis is that by using these botnets in a coordinated way, we can push the power grid into unstable states, triggering automated load shedding or tie-line tripping. Just to mention, so load shedding, if you haven't heard of it before, is the deliberate shutdown of electric power in part or multiple parts of a power distribution system to avoid a total blackout, right? So instead of, every power grid being in blackout, they can shut down one grid to save the others. The other name, tie-line tripping, is when the lines between two control zones trip. So because control zones are connected physically, if there is an overload on the transmission lines, then in order to protect the adjacent power grids, they'll trip the line, or basically disconnect it. This paper is focused on attacking power grids without relying on smart grid features. So, and I know in class we've talked about how smart grid has a lot of opportunities to attack because of all the connections, all the different attack vectors. But here we're just focusing on, power grids, basically doing a brute force attack, if you will. So there's a couple of different attacks that the authors are trying to test. So The first one's the static load attacks. The goal here is to increase the consumption of every bot in the botnet to the complete maximum in order to trigger load shedding. And this targets primary control. Attack 2 is a dynamic load attack, which uses the grid's closed loop delay. Remember, I talked about in the secondary control, it takes about 30 seconds for that to activate. So you're going to use that delay there to create a dynamic attack. And this can be used with attack 1 to amplify its damage, right? And then attack 3. So this one's pretty interesting. So the goal is to trip the tie lines by putting large loads on them. And how are we going to do that? So I have this, the authors have supplied this figure here, but to break it down, basically what happens is you'll put a very large load on, say, control zone 1, to the point where it needs help from another control zone. Let's call that control zone 2. Once control zone 2 starts to help control zone 1 by filling in that gap of energy, we will actually use the botnet to reverse which zone is in need of more power. So once control zone 1 is being helped by 2, we'll actually reduce the power on control zone 1, or the demand, and then we'll put all that demand on zone 2, which should eventually trigger a tie line trip. So what characteristics do we need to think about when we are gathering bots to attack power grids? So things like acquisition, right? How much is this going to cost us? Which, for a normal everyday person, probably a lot of money, right? But if something like a government agency were to try to do this as an act of war, it might be something feasible. Synchronization or speed. So if all the bots need to work together and we are trying to attack very quickly, we're going to have to know how fast it takes to, power up everything, power down everything, things like that. Also, geographical estimation, so location's pretty important for the third attack, because you're targeting 2 adjacent control zones. You're going to have bots that are inside of that location, and this geographical estimation is most important for attack 3, although it can be important for attack 1 and 2 as well. And then something else to think about outside of the bots is, how do we really know it's working? So if you're inside the control zone that you're attacking, you can actually just attach something to measure the frequency out of the wall outlet. That should help seeing the outcome of the attack. So in order to evaluate the effects of the attacks, we need to answer 2 questions. How much impact can a bot have to power consumption? And can we simulate the attacks? Because it would be unethical to actually attack a power grid. The authors decided to simulate these attacks using MATLAB and Simulink. We'll discuss that a bit later. And then we have to define what a successful attack is. So the authors define this as customers and or power plants being disconnected from the grid caused by load shedding, or transmission line ties becoming disconnected. And this is caused from overload protection or adjacent control zones disconnecting from each other, right? Tie line tripping. Okay, so since botnets are basically zombie computers, we're going to look at the effects that the computers have on the power consumption. So PCs and servers have a great potential for load control. The PC components, so like the CPU, the GPU, they don't directly draw power from the wall outlet. They actually, the PSU, which is the power supply, shown in this figure 3 below, receives power from the wall outlet, and it actually distributes the power to the components using DC to DC conversions and some capacitors to soften load spikes. So this is the model of the PCs that we'll be talking about a bit later. And then in order to plan the attack properly, the authors needed to measure the latency and the load of a few common devices. And so you'll see here, the latency is mainly talking about from the time we, tell the bot to turn on, I don't know, say, i3, the CPU i3, go to full power. How long does it take to reach maximum power? And then how much load is that taking up? A side note here, they found that laser printers actually take up the most power. So computers connected to laser printers were a big help to the authors as far as attacking with power consumption. Okay, so here's a model that was built in Simulink, and this is for attack 1. So a reminder that attack 1 is to quickly increase the demand of power to reduce the grid's frequency in order to cause load shedding. If the frequency decreases fast enough without the primary control being able to counteract in time, load is shed due to emergency protocol. Attack 2 uses the same model, but instead its goal is to use the botnet to draw its maximum load, wait for primary control to reach its maximum rate. Again, we're talking about that closed loop delay of about 30 seconds, and then stop all power consumption. This attack is more promising than the static attack. Since primary control's full activation takes about 30 seconds, the attack load is modulated as depicted here. And you'll see at minimal network power, the frequency gets pretty low because of an offshoot from the feedback, the control loop feedback. Now, attack 3, the goal is to increase the load in zone 1 beyond its capacity, wait for zone 2 to pick up the slack, and then just reverse the load, causing tie tripping. Here's the model that the authors came up with to test with. Okay, so how are we going to set up everything sort of like real life, right? There were 4 prototypical desktop configurations that were created based on the figures in the table below. So you have basically 4 types of PCs, an office PC, home gaming PC, and a server. And then for IoT devices, 2 scenarios were created. And I believe this paper was written in 2017, so the amount of IoT devices has likely gone up since then. But anyway, the first scenario uses only smart thermostats, and then the second scenario uses a mix of everything. Still pretty small numbers. So after the authors were able to simulate the attacks using their Simulink models, they found that depending on the mix of infected devices and other conditions, so which PCs they were using, how many IoT devices were connected to those PCs, also conditions like time of day and environmental, weather, temperature. They found that a successful attack can be achieved with 2.5 to 9.8 million devices. And while this seems like a very large number, it is definitely doable because of real-world botnets. So, in conclusion here, a couple things we learned, right? So, power grids are critical systems that use elaborate models to forecast supply and demand in order to stay in equilibrium. These models rely on assumptions that energy usage averages out at the macro level. And by using a botnet, it is possible to modulate power consumption enough to push these power grids into an unstable state, causing load shedding or line tripping. And here are the references used in the paper. And thank you.